velocity and acceleration. Bless you. The very neat application for this so-called R of t, this position vector, is that directly it consists of the x movement, the y movement if it's in the plane, and then if we're in the space, it'll be x, y, and z. From there, when you take the derivative of r of t, you get directly the velocity. Now, if it's a projectile motion, then we have to deal with the angle for the velocity. Take the second derivative of r, and we have the acceleration. Speed is said to be fixed, and so it's fixed as being, for whatever particular time, the maximum velocity is said to be the speed. And so we find the magnitude of r prime of t. So basically, in a nutshell, this is what we can glean directly from calculus to be able to find velocity and acceleration. What we also want to do is to talk about a projectile, a missile, or could be a baseball, if you will, a bullet, anything that's projected from a source has velocity, and the velocity through time is lost. And so we can calculate whether it's the initial velocity, or we can calculate the velocity after the initial movement, how that velocity changes. We can also calculate the maximum height, or any height at whatever particular time. We can calculate the distance. So the distance of the projectile would be the movement of x, and the height basically is the distance for y in a nutshell. But because of the angle theta, it gets a little bit complicated. So we'll look at that. I'll show you what Newton used, which was really first measured by Galileo Galilei when he was trying to measure objects in space, whether it's the moon, and trying to calculate its distance from the Earth, and then the movement of the moon with respect to the Earth in terms of the so-called velocity. So Galileo was able to, with precision, give us a number, a fixed number, for the gravitational pull. From that number, Newton took and was able to produce from it movement that gave the velocity, and then also to get back at the position of the initial movement of the particle. So we'll look at that, the way they examined it, and I think to me it's very straightforward. So here we have this projectile motion. If we start at some initial height, this projectile protrudes out of some initial position. And so we call this initial velocity v sub o. And then as we measure this, we could talk about this so-called maximum height. This particle, through time and with gravity, it reaches a maximum. Now that's the first derivative. R prime set to equal to 0. We have a maximum. We calculate that. And then it begins to fall. So I can look at the distance along the x-axis for the distance traveled, or we can look at the y-axis to look at the so-called height. We start with this gravitational number, 32 feet per second squared. We start with that as being the acceleration here of any object along the Earth. And from there, we can produce everything that we need. Yes,
32 feet per second. Is that on the fall? That's when it's falling?
yes, sir. Yes, sir. Yes, sir. That's the pull of any object in space pulling down back to the Earth.
What's going up to?
It's hitting it, but a stronger force that's acting on the projectile is the initial velocity. So what happens is that initial velocity, with respect to time, begins to topple out because it's being restricted by gravity, air resistance. If there is air resistance, typically there is. We would negate air resistance just for our discussion here. And if there's any other outside force that could also, bring it down a little bit quicker. So let's take this number using Newton's law that he has for force. Here we're concerned about here the acceleration being set to equal to this gravitational pull. And from there, let's see if we can build velocity and also build the position vector. So let's take the same diagram here. Let's see if we can relate it here with the angle theta, and then the distance along the x-axis for x is I, or with respect to the x-axis, and then the height y, the initial velocity. So now what we do is when we look at that, so we have the cosine theta is x over the so-called initial velocity. We measure it. It's some measurement. And so we have x is equal to this initial velocity times the cosine theta. And then if I take the sine of theta, I have the opposite, y over the hypotenuse. And so we get y is equal to this magnitude of the initial velocity times sine theta. And so here we said that this velocity is equal to here this movement of x also plus the movement of y. Well, x is said to be the initial velocity here times the cosine plus now. So we look at this, but we say that the true velocity is determined if I'm calculating this so-called true velocity, or if I'm calculating the so-called true distance, x. I need to incorporate, with theta, I need to incorporate time, because time is a strong factor. Why is time a factor? Well, because we know that the so-called rate is equal to the distance divided by time. That is, this velocity is equal to some distance x divided by t, and so we end up with x is equal to some velocity times time. Right? And that same is also applied for y too. So also y, its distance, is also found by some velocity with respect to time. So here, now I want to go a little bit further, and what I want to do is to produce this guy without even memorizing it, because that's a little bit too much for my brain to hold. So here's what we have. Let's see if we can add a page in there. And so we let the acceleration equal to 32 feet per second squared. And I'm going to negate it, and looking at here this this decreasing value with respect to gravity. And so let's say that A is equal to negative 32 feet per second squared. Is it true that if I take the integral of the acceleration, that gives me velocity? Okay. We have a constant, by all means, yes. So this becomes AT plus C sub 1. So here we have velocity is equal to negative 32t plus C sub 1. Let C sub 1 is a velocity. Do you agree with me? Because it says the velocity is equal to velocity, right? So C sub 1 is a velocity. It becomes the initial velocity. So here we have V is equal to negative 32t plus the initial velocity. Is it also true that if I take the integral of the velocity, I have the position or the distance, x here, this would be r. Right? So r of t is equal to the integral of v dt. So this is the integral of the negative 32t plus the initial velocity dt. So r of t is equal to negative 16t squared plus the initial velocity times t plus some, let's call this c sub 2. But c sub 2 is a distance. C sub 2 is a distance. Look, again, velocity times time is a distance, right? See that? Rate times time gives us distance, right? This negative 16t squared. We would see this a lot in algebra class, a long time ago. And you wondered, I don't know if you did, but I did, where did that number come from? Well, it came from the negative 32 feet per second squared, taking the integral twice. Well, they couldn't tell us that back in 10th grade, right? Well, maybe they should have, and we would have actually known what was happening. So here, c sub 2 is the distance, distance. So we set c sub 2 to equal the initial height. You can call it R naught or H naught, if you will. Doesn't matter what you call it. So here, R of t is equal to negative 16 t squared plus this initial velocity times t plus, let's say, r naught. This represents the y component. Okay. So if that's the case, then we have here r of t, we said was this x movement plus some y movement. Need more space there. This r of t becomes, in terms of the so-called x movement, this becomes the initial velocity times the cosine theta. And to get x, I got to multiply that velocity by time. Plus, I'm going to write this negative 16t squared plus that initial velocity. Initial velocity is traveling, it's on the other page. This initial velocity here travels with the cosine for x. This initial velocity for y travels with that sine theta. And we had the t in there already, times t. And then this is plus that initial height, r naught times j. So here I get the so-called the x movement and then the y movement. We get that from the acceleration equal to negative 32 feet per second squared. That's the formula. And thus, we do not memorize it, we just derive it. Now, with that said, let's look at a problem. So here, first find the velocity, the speed, the acceleration vector. Evaluate the velocity and acceleration vectors at the given value for the time t. So we said that the velocity, v of t, or just v, is equal to r prime of t. Just take the derivative straight forward. So it gives us I plus 5j plus 3k. Even at the value t equal to 1, here this velocity is fixed, it's constant, so it remains the same. And then now we find the acceleration. Here that's said to be r double prime of t, and that's 0. What about the speed? Speed is said to be the norm of the velocity. So this is the square root of, we take the velocity, we take the components thereof. So this implies that here x prime is equal to 1, y prime is equal to 5, z prime is equal to 3. So this becomes x prime of t squared plus y prime of t squared plus z prime of t squared. So that just gives us 1 squared plus 5 squared plus 3 squared. That's the square root of 1 plus 25 plus 9. Just the square root of 35. So that's all we do there, right? So just very direct. All right. For this problem, why don't you find the velocity, the speed, and acceleration, and then find those values at the given value for t equal to 4. Well, let's see. How does that look? So for the velocity, um, and I didn't find them at t equal to 4, but for the velocity, I get I plus, that would be 8j, right? Plus 4k for the velocity. No, sir. No. You put the t equal 4 in after you find the velocity. If not, then you just get 0 for your velocity, right? That's the square root. What'd you get for the speed when you plugged in? You got 9. good. Okay. Yes, sir.
Do you want us to solve for it, or do you want math, or input, or which way do you want it?
Um, well, you do two things. First, you find the velocity, the speed, and the acceleration, and then you evaluate them at the given value for t. So I just forgot to evaluate mine at t equal to 4. So, yes, sir. So you find v, and then you evaluate it at the value for t. Good. What about that one? Is that the same one? Am I going crazy? Oh, I didn't go. I went backwards in my hitting my pen. Okay. I'm not going crazy. All righty. So here use the model for projectile motion, assuming that there's no air resistance, and g is equal to, it's supposed to be negative. So let's list what we have. It says that a baseball is hit from a height of 2.5 feet above the ground. So that's R naught. The initial height is 2.5. With an initial speed here, initial velocity of 140 feet per second at an angle theta 22 degrees above the horizon. Here, find the maximum height. Well, that means find y, its maximum height. Reached by the baseball. Determine whether it will clear a 10-foot high fence located 375 feet from home plate. All righty. So let's see. So what we have here is, if we look at the image of this, so this theta here is the 22 degrees. They give us the initial velocity. That's 140. And then the initial height, this guy is starting off .5. So we want to find here the so-called maximum height. Let's look at what we have and look at what we can write out. X here is equal to this initial velocity times cosine theta times t, the so-called time. They tell us that x is 375 feet. So that's the so-called distance traveled. So 375, that's equal to the initial velocity of 140 times cosine, and here the cosine of 22 degrees. That's times t. And from there, we can solve for t. So t is equal to 375 over 140 times the cosine of 22 degrees. Do not see my calculator here. Can you calculate that? Okay. So here we get the time is 2.8 seconds. That's 2.8 seconds for this baseball to be hit, and as it travels all the way over this distance of 375 feet. 375. Yes. Oh, thank you. I used to keep like 3 or 4 calculators down here, but yeah, I like that one. Thank you. Appreciate it. So in 375 feet, this baseball goes from the initial point and then it comes back down here, and it does that in a total time .8 seconds. But I need the time when it's here. That's that total height. Because it says find the maximum height reached by the baseball. So we need to find y at its highest point. Well, let's see. This is y equal to negative 16 t squared plus the initial velocity times sine theta times t plus the so-called initial height. This is y equal to negative 16 t squared plus the initial velocity. They give us that to be, was it 140? 140 times sine of 22 degrees times t plus 2.5. So to find the maximum height, I simply find the derivative for y. Find y prime set it equal to 0, because when the derivative is 0, that means that the derivative or the slope is horizontal, right? That gives me that crescent. So we set y prime equal to 0. Here the goal is to solve for t, to solve for that time. Once I have the time, when it's at its maximum height, I take the time and put it back into the function or the formula for y. And then that'll give me the height. So let's see. So here we set y prime equal to 0 to solve for t at its maximum height. So y prime is equal to negative 32t plus 140 times sine of 22 degrees. We set that equal to 0. Well, this implies then that t is equal to negative 140 times sine of 22 degrees all over negative 32. Brother Donnie, I'm assuming that this is set for degrees. Let's see. I think it is. I think it's set for degrees and not radians. I get 1.6389. Is that what you get to? Good deal. 1.6389 seconds. I'm going to take that value and plug it in for y. So here, to find the maximum height, implies that we have y evaluated at 1.6389. That's equal to negative 16 times that time, 1.6389 to be squared, plus the initial velocity, 140, times sine of 22 degrees, times 1.6389, plus the initial height, I think that was 2.5. So we get y. Let's calculate that. And you can truncate that time if you want, maybe 1.64. You may be able to get away, with that. Let's see. So negative 16 times 1.6389 to be squared, plus 140 times 1.6389 times that sine of 22 degrees. Then that's plus 2.5. We get 45 point, let's say 48 feet. Is that what you get? $45.48. Got that too. Good deal. All right. Is everybody okay with that? And then it raises the question, when that, it says find the maximum height reached by the baseball, determine if it will clear a 10-foot high fence. Yeah, it goes up 45 feet, above that. So yes, it's going to clear it. Yeah. That ball, when it goes out, there is maximum height. So I think we're good. What about this next one? See if I can find it. This guy right here. A baseball hit 3 feet above the ground, leaves the bat at an angle of 45 degrees and is caught by an outfielder 3 feet above the ground and 300 feet from home plate. What is the initial speed of the ball and how high does it rise? So you want to find the initial velocity and the maximum height. Try your hand at that. Let's see what you can get. Now, the best thing for me is to just try to draw out some kind of image, just so that you kind of get an idea of what's happening. And obviously right here would be the so-called maximum height. This distance is 300 feet. If I were you, I would try to go in this order. First, find the initial velocity, and then use the initial velocity to find the maximum height.
You just said the initial height was 0. Correct.
see if I can give you some more pointers to it, and by all means, I'll let you finish. Let's see. So we know that x is equal to the initial velocity times cosine theta times t. Well, they give us x to be 300, is that right? So x is 300. We don't know the initial velocity. We don't know the time, but we do know cosine theta. So cosine theta, that's cosine of 45 degrees. So here, that's the 300 is equal to the initial velocity times the time times 1 over the square root of 2. That's a 3. It's a 3. So we have 300 times the square root of 2 is equal to the initial velocity times the time. So we have that so far. That's good. So now, if I come up and if I look at here, this formula for y, which is the negative 16 t squared plus it's the initial velocity times the time times sine theta. That's plus the initial height. I believe that was 3 feet. Good. Then it tells me that when this guy travels the distance of 300 feet, an outfielder catches it, and he's 3 feet above ground. So when I look at that, I have negative 16 t squared plus the initial velocity times the time times sine theta plus 3 is equal to 3. So what I have is this. I have negative 16 t squared plus the initial velocity times the time. That's directly 300 times the square root of 2. And this is times sine theta. Well, that's 1 over the square root of 2. This is equal to 0. Subtract 3 on both sides. So I get negative 16 t squared plus 300 is equal to 0. That gives me t is equal to the square root of 300 over 16. Well, this is the square root of 100 is 10. The square root of 16 is 4 times the square root of 3. So this is 5 times the square root of 3 all over 2. Well, if that gives me the time, then I can find the initial velocity. So if 300 times the square root of 2 is equal to the initial velocity times t, that is, the initial velocity then has to be 300 times the square root of 2 all over t. So the initial velocity is 300 times the square root of 2 all over 5 times the square root of 3 all over 2. So this is 2 times 300 times the square root of 2 over 5 times the square root of 3. And this is 2 times 300 times the square root of 6 all over 5 times 3. So the initial velocity looks like 40 times the square root of 6. Okay, I found the initial velocity, so you got to find the height, right? again, how do you find the height? Talk to me. Just talk to me with words. How do I find the height? Huh? The equation with the sign in it, you do what with that? That won't give you the height though, because if you take the formula for y and just plug everything in it, that's going to give you 0 for the height. Because that formula for y is measuring the whole movement of that baseball, right? As it starts, it rises and it falls. So here that total time there will give you a height of 0 or 3, since the outfielder caught it at 3 feet. He's 3 feet above the ground. So how do we find that maximum height? The maximum height is at what value on the graph? It's where? Okay, and what happens there? The derivative is equal to 0. So to find the maximum height, I take y, find y prime, set it equal to 0, and that gives me the time at the maximum height, right? So when I solve for that, I get time at the maximum height. Take that time t and plug it into y equal, and that gives me my height, my maximum height. Okay. All right. I'm going to leave that with you. I'm going to move on. Look, I can give you the answer, show you that, so you know what you're working toward. So that maximum height is going to be 78 feet. So when you work that out, that's what you'll get. Okay. So I'm going to stop here, and we'll take just a 5-minute break so I can get set up for section 12.4.